Let's review the deployed SRv6 use case as of February 2020. The first use case is VPN over best effort 5G slice. That's a very simple use case, and the network program to execute it is only requiring one single instruction. So let's review it step by step. Node number 1 is the ingress P, node number 3 is the egress P. All what we need when we start this is a basic IPv6 forwarding in the network. Only node number 1 and node number 3 are SRv6 enabled. A customer packet gets to node number 1. Node number 1 does a lookup in a verb. It realizes that this route has been advertised via egress P number 3. It adds another IPv6 header, and in the destination address of the other header, it writes the segment B3v9. What does it mean, B3v9? Let's imagine that in this deployment, we have allocated the block of address, let's say B/40, for the SRv6 services. And let's imagine that we have allocated B3/64 for the locator of node 3. So it means that node 3 in ISIS is saying, hey, B3/64 is me. So it basically means that within that the network, everybody is computing a best effort shortest path to node 3 for any packet that is destined to B3/64. So once we have done this IPv6 encapsulation, that we have written the destination address, the packet is sent by 1 and then forwarded by 2 along the best effort shortest path to node 3. The packet gets to 3 and 3 says, look at it, and it says, the first bit's B3, that's me. So I am able to understand the remaining 64 bits. And this I am able to decode that it means a function that is a VPN function that is to decapsulate the packet and look the inner transported packet in the table 9. And that's it. We have very easily realized a VPN service over a best effort 5G slice. This has required no segment routing extension header. Now, let us look at another use case that is deployed as of now. It's VPN with low delay 5G slice with the Flex Algo option. I think 2-3 years ago, we unveiled for SR-MPLS the notion of Flex Algo that we could also call custom algo. That's basically the ability in ISIS to customize algorithm the way you want. This is not the IETF that is going to tell you how to do it. You do it yourself. And this Flex Algo, this customized algorithm, start at the so-called algorithm number 128 up to 255. So you have plenty that you can define yourself. So let's say that we are going to define the algorithm 128 in this ISIS deployment to be a shortest path based on delay. Yeah, but delay what it is. But actually 2-3 years ago, first in the context of SR-MPLS, but now as well for SRv6, obviously this is the same technology. So we are leveraging all of these functionalities. We are able to measure continuously the unidirectional latency of every link. Not only are we measuring it, but we are reporting it in ISIS. And we are reporting it according as the delay metric of the link. And that's it. Now, all my nodes, they run two algorithms, the best effort by default algorithm of ISIS that would compute the shortest path according to the best effort metric of ISIS, but as well a shortest path to a node according to the Flex Algo 128 that is defined to be a shortest path on the measured delay, and the delay being continuously measured by every router and updated in ISIS. And so we now see that it's quite easy. In my deployment, I simply allocate another block of segment, let's say the D block. And in that D block, I'm going to give the locator D3/64 to node 3. And so when now I have a customer packet that comes at ingress P number 1, and I do a verb lookup, and I realize that the egress P is 3, but that the SLA of this service is not to take the best effort path through the network, but to take the low latency path through the network. Node number 1 is going to encapsulate the customer packet in another IPv6 header where the destination address is D3v9. Indeed, the packet will follow the D3 locator that is computed according to the algorithm 128 along the green arrow you see on this picture, avoiding the bad delaying. The packet will get to node 3. Node 3 will say, hey, D3/64, it's me. So I am able to decode the function in the remaining bits of the instruction that is in the destination address. And I see that this is a VPN function, so I decapsulate and I look up the inner packet in the VPN table number 9. And so be it. We have basically executed a VPN over low delay 5G slice in a very easy way. I just had to encapsulate it in IPv6 with just the destination address carrying one single instruction. I don't even need a segment routing extension header. And this is shipping and this is deployed. So now let us look at Snort firewall insertion. I would like to do a low delay slice. I'd like to do a VPN, but I would as well to integrate an NFV service in my network program. Now, basically, my network program will require 2 instructions. And so when the ingress P will receive the customer packet and that it will map it to its policy, is going to encapsulate the customer packet in an other header where the destination address will hold the first instruction, which is D2 Snort, and there will be a segment routing extension header with one additional instruction that is D3v9. The packet will be sent along the shortest path to D2, which is the low delay slice to node 2. When 2 gets it, he says D2, it's me. I'm able to understand the function. It says Snort, so I give the packet to the Snort VNF. The Snort VNF does its work. The packet gets back to 2 with the destination address modified to hold now the active instruction D3v9. So 2 and 5 route according to the low delay slice of the 5G network up to node 3, where 3 says, hey, D3, it's me. I'm able to decode the function. It says VPN, so I decaps and I look up in table 9. And that's it. We have the realization of what we have explained it as our target. The integration of any aspect of a network solution in the same powerful solution. We can instantiate VPN services, we can instantiate traffic engineering services, we can instantiate VNF, all in the same powerful solution. And you see here that all of that VPN, the low delay slice and the integrated NFV only requires an SRh of 1 instruction, because in total I only need 2 instructions. So it's very powerful. And as we will have more time to describe this, you will realize that this is extremely powerful at the scale of 5G. Why? Because this low delay slice, the D2 Snort, the D3v9, it works across domains because it's the power of SRv6 summarization. So if you want to extend this not to a single domain as it is described here for simplicity, but if you want to look at it across multiple domains at ultra scale with 100,000s of routers, the same scalability approach will be reached. And so it's extremely powerful. Deployed use case as well, optimum load balancing day 1. After 20 years of MPLS, MPLS still has issues with load balancing. Why? Because in MPLS, the entropy to do the ECMP selection is in the IP packet. And so the hardware needs to dig down through the label stack to find the IP header and hash on it. With SRv6, day 1, we make it much smarter. What we do is that the ingress P anyway looks at the customer packet. And so the ingress P computes a hash on the customer packet and writes it in the flow label of the added IPv6 header. Much smarter. The ingress P does it, so it's no additional work for it. And when he adds the other header, he writes the entropy in the flow label. So the remaining of the network, in order when they have an ECMP selection, they can just use the other header. There's never any need to dig down through the layers of encapsulation to find the entropy. And so it's a day 1 delivery, and this is deployed. So If we would have more time, but I'm going to try to give an intuition to this. SRv6 enjoys a very strong seamless incremental deployment, and that's proven by fact. We started this publicly in 2017, and already in beginning of 2019 we were deploying. So it means that the seamless deployment capability is really present. So if you look at an SRv6 VPN service, all what you need to do is to upgrade the PEs. The core of the network can do simple plain IPv6. If you want to then add traffic engineering services, you don't need to deploy SRv6 anywhere. You only need some traffic engineering waypoints at some specific location in the network. And so these few well-selected points can be your SRv6 upgrades, and later on the SRv6 step-by-step is expanded through the network. Same way for fast reroute, it's very well known. TLFA is a per router capability. This is the way we invented it, engineered it. It has become now widespread in the industry, and this is a node-by-node functionality, so it can be deployed incrementally. This is so obvious that sometimes it can be forgotten. SRv6 enjoys prefix summarization. With MPLS, that native, obvious functionality of IP had been lost, because in MPLS you cannot summarize. You need to lead the specifics. And that led to very complex inter-AS option A, B, C, and all the BGP 3107 design in large-scale deployment. In SRv6, all of this is deleted, forgotten, no more. Why? We get back to pure IP. And so if in Metro number 1 I have hundreds of thousands of /64 locators because I have hundreds of thousands of routers that are SRv6 capable, I only advertise a single summary to my core. If in Metro 2 I have hundreds of thousands of SRv6 routers, each with their locator, I only advertise a single summary to the core. So my core now is only carrying the locators of the core nodes and the summary of the Metro, a few hundreds of routes. And so it's extremely powerful. As we saw in this review of deployed use case and capabilities, SRv6 has excellent native scale. Many use cases do not even need a segment routing extension header. If you look at any VPN constructions, if you look at EPE that was very nicely described by Facebook and Google at SIGCOMM 2018, EPE does not require SRH. If you look at the low latency or disjoint slicing for 5G across multi-domain networks do not require SRH. If you look at optimal load balancing, you do not need any SRH or any other protocol, etc. It's in the other IPv6 header. And if we need an SRH, in most cases you will need one or two segments or instructions additional to build your network program. And we saw that we had the prefix summarization gain. So excellent native scale. On top of the inherent simplicity of the solution, we want to prove it, and that's why we are always delivering with our SRv6 solution an automation package. We are always, not always, but what I want to say is that from the start we have this automation package, and this automation package takes care of automating the address allocation for the loopback for the physical interface, the SID allocation for algorithm 0 and the flex algo. It does it in intra-domain or multi-domain. It does the ISIS summarization and redistribution between domains. It automates the configuration of latency measurement. It deals with the additional configuration of the flex algo for the delay slice. It enables TLFA. It enables BFD for liveness of the links, and then it enables the BGP VPN-based services. And so the key point is that if you don't use NSO, it's not to position the NSO solution here. The key point about this slide is to say the automation of SRv6 is very important. As and is very simple because the SRv6 solution itself is very simple. So we take a great care of this, and our experience is that it's quite easy to automate it. And so either you can leverage the NSO feature pack if you're interested, or you basically build your own automation system. What you have to know is that the native simplicity of SRv6 is going to make your automation much simpler than any than other experience you may have. So another review of the deployed use case, and here we really thank Iliad for sharing some specific of their deployments. They deploy SRv6 in their network with a subblock of FC/8, which is the private block available to anybody for their private deployment. And they do all the SRv6 solution across the different networks with a /40. So it's basically they are using 1/billionth of what they could use. So everybody can use FC/8. They use it, obviously. And to do SRv6 across the different networks, they only use 1/billionth of the FC/8. So absolutely negligible. And we thank Sébastien for sharing this information that allows everybody to see that SRv6 seed block allocation is completely not using any important address space. If we thank as well Satoru-san for sharing the SoftBank practice, the SoftBank deployment for all of the SRv6 services is based off a /40 out of the public /20 block received from Apnic. So they are using for all of the SRv6 services 1/millionth of their current IPv6 blocks. Absolutely negligible. So many thanks to Sébastien from Iliad and Satoru-san from SoftBank for sharing the specific of the deployment to really show that the SRv6 seed allocation for the network programming is absolutely insignificant compared to the IPv6 address space that is available either through private block or public block. This presentation is available at this link, and in the next few weeks we may add other videos on the SRv6 solution update. Many thanks.